Berkeley, 1973. The graduate school's numbers go public. 44% of men admitted, 30% of women. A lawsuit takes shape. The bias looks undeniable. It is right there in the totals. Then a statistician splits the data by department. And inside the departments, the story flips. Women are admitted at equal or higher rates almost everywhere. Same data, two opposite verdicts. Both sums correct. Welcome to the most dangerous illusion in statistics, one that has misled courts, hospitals, and headlines, and is quietly hiding in a table near you. The illusion has a pedigree. Carl Pearson brushed against it in 1899. Udny Ewell mapped it properly in 1903, 50 years before the man it was named after. Edward Simpson's 1951 paper made it famous with one unsettling observation. A treatment can look helpful in the whole population, harmful in every subgroup, or the reverse, using the same, perfectly correct numbers. Statisticians call it the amalgamation paradox. The act of merging tables is itself an operation, and it does not preserve conclusions. Half a century of warnings. Berkeley still surprised everyone in 1973. Here are the real numbers, 6 departments, published in Science in 1975. Department A, men, 62% admitted. Women, 82. Women ahead by 20 points. Department B, women ahead again. D and F, women ahead or even. Only C and E tilt slightly toward men. Add it all up though, and men lead by 14 points. Every department can favor women, while the total favors men. The arithmetic is not broken. Something else is going on. Before scrolling on, try to guess the mechanism yourself. The answer is not in the percentages. It is in a number we have not shown you yet. The trick is where people applied. Department A admitted most applicants, and its pool was overwhelmingly men. Departments C and E admitted almost nobody, and that is exactly where women applied. Men, on average, knocked on easy doors. Women knocked on hard ones. The total does not compare men and women, it compares doors. Aggregation quietly swapped the question, and the answer flipped with it. Watch the widths in this picture, not the heights. The widths are where the verdict was decided. Here is the machine that does the flipping. A total admission rate is a weighted average. Each department's rate, weighted by how many of your people applied there. Picture a number line from 0 to 100%. Place a weight at each department's rate, heavier where more people applied, and the total is the balance point. Men's weights pile up on the high-rate departments. Their balance point settles at 44. Women's weights sit on the low-rate departments. Same rates available, but the balance tips to 30. Move the weights, not the rates, and the verdict moves with them. That is all a total ever was, a balance of weights. This is not a one-off. Medicine, 1986, 2 treatments for kidney stones. Open surgery, wins on small stones, 93 versus 87%. Wins on large stones too, 73 versus 69. Better in every single case you could face. Yet in the overall success table, the other treatment looks superior, 83 to 78. Because surgeons save the hard, large stones for open surgery, and hard cases drag averages down. Better everywhere. Worse overall. If you were the patient, the choice is clear, and it is the opposite of what the totals say. See the geometry of it. Draw each group as an arrow, across the number of cases. Up the successes. The slope of the arrow is the success rate. Now chain the arrows tip to tail. Two steep arrows can add up to a shallow total if the steep parts are short and the shallow parts are long. Slopes do not average like numbers. They average by weight, and the weights are where the paradox hides. So which story is true, the total or the parts? The honest answer, it depends on what caused the split. If departments choose their own bars, the fair comparison is within each department. Split. If a doctor assigns treatments by stone size, size is a confounder. Split. But if the grouping happens after the outcome, or is caused by the treatment itself, splitting can lie just as badly. The data alone cannot decide. You must know the story behind the columns. The strangest documented case involves cigarettes. Wickham, England, 1970s. Over 1,000 women surveyed, then followed for 20 years. The survival rates came out backwards. 76% of smokers were still alive, versus 69% of non-smokers. Smoking apparently preserved life. Split by age, and the story writes itself. Within every age band, smokers fared the same or worse. The catch: the smokers were simply younger. Young women smoked. Old women never had, and youth, not tobacco, did the surviving. Any headline built on the merged table would have been perfectly wrong. How often can this actually happen? Simulate it. Build 1,000,000 random 2x2 studies, random rates, random group sizes, and check each one for a reversal. The answer: about 1 to 2% of tables flip. Rare enough to feel exotic, common enough that any newspaper, any hospital, any year of court records almost certainly contains a few. 1 in 60 is not a curiosity. It is a base rate, and nobody is checking most of the tables. Once you see it, it is everywhere. A batter can trail another player in both halves of a season and lead for the year. A school can raise every group's test scores and still watch its average fall because its intake changed. Wages can rise in every sector while the national average sinks. None of these are lies of arithmetic. They are truths about mixtures, and mixtures are what most statistics are. Every average you have ever read was a mixture, wearing a single number as a mask. One table, two true summaries, opposite signs. The total answers one question. The parts answer another. Simpson's paradox is not a flaw in mathematics. It is mathematics refusing to let a single number tell a mixed story. Whenever someone hands you an average, ask what was averaged over. The reversal is always hiding in the weights. 1 in 60 tables carries this trap. Now you are one of the few who checks. The whole can contradict every part.